All right, so this is going to be chapter 6.2, and we're going to be starting talking about quadrilaterals, so specifically parallelograms. The next couple sections are going to revolve around parallelograms. So let's begin by kind of defining what that is. So a parallelogram is a quadrilateral with two pairs of parallel sides. To write the name of a parallelogram, we use a little symbol, a little parallelogram symbol, and then the points. So here below we have a parallelogram, which is called ABCD, and you can see the two sets of parallel sides. So AB is parallel to CD, and BC is parallel to AD. And that's what we have written here. We're going to call this our defining characteristic of a parallelogram. Technically, this is a property that does lead us to some different things. Anytime we have parallel lines, we need to be looking for things like alternate interior angles or same side interior angles, or all those different things that we learned about in chapter 3. But yeah, this is the defining characteristic. So anytime you're trying to demonstrate to someone that you have a parallelogram, this is what you're going to try to show. It's also a property. All right. So properties of parallelograms, here's number one. So if a quadrilateral is a parallelogram, then its opposite sides are congruent. So that means that AB and CD are congruent. They're opposite. They are across the shape from each other, right? Across the shape. That's what we call opposite. And BC and AD are also congruent. Now, this is not too hard. I'm going to kind of briefly talk about what a proof of that might look like. What it's going to look like is this. If we draw a diagonal, doesn't really matter where, but draw a diagonal through our parallelogram, we end up getting some angles here, some angles that are actually not part of the original parallelogram, but are angles. So this angle 4 and angle 3 would be congruent because they are alternate interior angles. They're between parallel lines and on different sides of a transversal, which is this diagonal that we drew. And it's also true that 1 and 2 are congruent for the same thing. They are between some parallel lines, LM and JK, and they are on different sides of this transversal, the same transversal. So we have two sets of congruent angles, and then the diagonal itself is actually obviously congruent to itself. So that actually helps us show that these two triangles, JKL and LMJ, so this triangle on the left, upper left, and this triangle on the lower right, are congruent by ASA, angle, side, angle, angle, side, angle. From there, it is very easy to then use CPCTC to say, well, that means that LM and JK, those are corresponding parts. Since these triangles are congruent, they have to be congruent. And it's also true the same way here that LK and JM, they are corresponding parts, and these triangles are congruent, so therefore they have to be congruent. Again, we're making use of CPCTC here. Not too difficult. This isn't a full formal proof, but we did walk through kind of the important ideas. I'm going to try to do that for most of these properties. Okay. Here are the next two properties. So we have the opposite angles are congruent. So angle B and D, angle A and C. Opposite means they are kind of across the shape from each other. So easy enough, A and C diagonally across, B and D diagonally across. Again, very similar idea. If we sketch in a diagonal, it's really easy to show that these two triangles are congruent to each other. Therefore, B and D are congruent by CPCTC. And then if we draw the diagonal the other way, it's easy to show that these triangles are congruent, again, by ASA, and that makes these corresponding parts. Pretty simple proofs. Multiple steps, like they're not super easy. They're kind of some of the harder ones we did, but they are basic CPCTC proofs. From there, the next property, I guess we're numbering these as number 2, 3, and 4. So property 3 here is that the consecutive angles are supplementary. So consecutive angles are angles that are next to each other as you go around the figure. So A and B would be consecutive, B and C would be consecutive, C and D would be consecutive, and A and D would be consecutive. This is really easy. This is literally just same side interior angles. If I expand these out, it's a little easier to see. So here are our parallel lines. Here is our transversal, same side interior angles. Pretty easy. I could do this for all the different sets, but it's just same side interior angles. No fancy proof necessary. All right, and then the fourth property, 2, 3, 4. Fourth property is that the diagonals bisect each other. So diagonal BD and diagonal AC cut each other in half. So this and this is congruent, and this is congruent. Now, this one is a lot more complicated. Again, it's all just based on showing that we have some congruent congruent triangles. So I could kind of illustrate this sort of quickly here first. So let's focus on just one of the diagonals. So I'm going to focus on AC, or I'm sorry, not the diagonals. Let's focus on one of these sets of two triangles here. So this triangle down here and this triangle here, one in black and one will be in red. So it's pretty easy for us to show that these triangles are congruent using some combination of the things we've already done, like these two sides are congruent. We already know that. That's property 1 that we went on in the last page. Similar idea here. We could say that this angle and this angle are equal because of alternate interior angles. We have vertical angles here and here. So a couple different ways we could show that these two triangles are congruent. And that means that these parts, which correspond to one another, would have to also be congruent. So BZ, ZD would have to be congruent because they're corresponding parts of congruent triangles. So then we would kind of flip this around and we would do the same thing for these other two triangles on the left and right of this shape. And the same thing happens for us to demonstrate that. Pretty easy. I say pretty easy. It's actually not that easy, but it's basic ideas that we have learned about in the past. Nothing new that is going on there. We're just applying it in a new context. Okay. So here's a quick summary of those 4 properties. So this is property 0. This is our defining characteristic. So I'm calling it property 0. Doesn't really matter. And then these are the 4 that we just kind of ran through quickly. Opposite sides are congruent, opposite angles are congruent, consecutive angles are supplementary, and the diagonals bisect each other. These are really the properties. This is really the definition, but we'll list it as a property as well. Okay, and yeah, let's go ahead and, this was an interactive slide, but let's go ahead and mark out some, let's see, blue is supposed to be opposite congruent angles. So A and C would be an example of that, or B and D. Easy. An example of consecutive supplementary angles would be like A and B. Consecutive, they're next to each other, and they are supplementary. Or A and D. It's another option. Or D and C. Another option. B and C. All of those would be options for that. Ooh. Take a second to look at this, pause it, and try to answer this question. Which equation is true in parallelogram JKLM? So take a look at these two equations. Let's see which one's true. All right, hopefully you noticed that it was this one based on these sides. The opposite sides are congruent, so these two things are equal. This one is not true, or at least not necessarily true. It could be. I mean, if all we know is that it's a parallelogram and we don't trust the picture too much, this could be true in one specific case, but in general, it's not. These two angles are actually supplementary because they are consecutive angles. So they should actually add together to equal 180. That should be the correction for this one. Okay. And now we could solve these, and if you wanted to do that, we could actually solve them, right? We could solve for x, figure out these side lengths, and we could solve for z, and we could figure out all of our angles. I'm actually going to take a second and solve for z just to show that real quick. I know that wasn't even the correct equation, but I'm just going to do it. So 5z minus 6 plus 2z minus 3 equals 180. So combine like terms, 7z minus 9 equals 180. 7z equals 189, and then z 189 divided by 7 is 27. So 27, let's go ahead and find angle L. So that would be 2 times 27 minus 3. That makes this one 54, also 54, right? Opposite angles. And then supplementary to that would be 126. And we should get the same thing over here. I'll just quickly do that. 5 times 27 minus 6, just to verify. Oh, I misspoke. I don't know why I did that. I do all that work and then I write down the wrong number and say the wrong number. This was 51. 54 minus 3 is 51. 51. And then these were all both 129. Sorry about that. Anyway, the point I'm trying to illustrate here is if we know one angle in our parallelogram, we can find the rest of them. Okay, let's go ahead and move forward. Let's find the angle measures. So here we go. Here is an example of what I was just talking about. If we know one angle, we know the rest, right? These are equal. So y is 61. These are supplementary. So that's 119. So 119, 119. If you know one angle in your parallelogram, very quickly can find the rest. There's only 2 different measurements. This gets a little more complicated when we have a diagonal involved and the angles that are created by that diagonal, but still pretty easy. There's a couple things to do. This is 53. This is 53. Opposite angles. Now from here, we can kind of split some things up. This is a triangle, so 53 and 90 and whatever this is, right? So 53 and 90 come together to be 143. So if I do 180 minus 143, that is 37. So this is a 37-degree angle. And now we can kind of start unlocking things. Angle Y is alternate interior to this angle. So this would also be 37. And this 90-degree angle is alternate interior to X. So X would also be 90. Pretty simple here. Again, we can make use of the triangles. We can make use of the parallelogram properties. It's all pretty basic once we get some information about it. Okay. And now last example here. Here we have the diagonals. So we do need to keep in mind that the property at play is that the diagonals bisect each other. They cut each other in half. So this diagonal is cut in half. This diagonal is cut in half. They are not equal. One of the diagonals is longer than the other, but the halves are equal. So we actually have 2 separate equations to write. 4z minus 9 equals 2z. That's this one here. And then 3w equals w plus 8. So with those 2 equations, we can solve, let's see, we're looking for FH, which is our whole diagonal length here. And we're also looking for EG, okay, which is the other whole diagonal length. So let's go ahead and solve these 2 equations. I'm going to put all my x's on that side, so I'll subtract 4z. That gives me negative 9 equals 2z. Divide by 2 equals negative 2z. Divide by negative 2, I get 4.5 for z. Okay, 4.5 for z, so that means this is 2 times 4.5, so this is 9, and this is 9, so FH is 18. 18. Okay, going ahead and solving the other side as well. I'm going to put my w's over here, so minus w. I get 2w equals 8, or w equals 4. Okay, so here we go, 4 plus 8, this is 12. This is 12, so our whole diagonal would be 24. Not too bad. We need to remember our properties though. Make sure to go back and look at them if you don't have them. If you don't see it right away, kind of take a look at the different properties that apply to the shape you're looking at and see if something helps. All right. So make sure to do the 6.2 homework that's listed on our agenda, and I'll see you guys later.